Let's start with a cat that's dead and alive. You're in a tiny lab in 1930s Europe, staring at a steel box on a table. Inside, there's a cat, a vial of poison, a hammer, and a single radioactive atom that might decay or might not. If it decays, a detector triggers a hammer, smashes a vial, and the cat dies. If it doesn't, the cat lives. You close the lid and walk away. Minutes pass. The room is quiet. No meows. No thud. Nothing. According to the quantum rules, everyone's arguing about that atom isn't decayed or not decayed yet. It's in a weird both-at-once state called a superposition. And because the cat's life is hooked to that atom, the cat is now in the most cursed status possible. Not alive, not dead, but both. Here's the twist. Until you open the box and measure what happened, the math says the system has to be treated as a mixture of both realities at once. Your everyday brain screams, "Come on, the cat is either dead or alive, we just don't know yet." Quantum mechanics shrugs and says, "Nope, the universe literally hasn't decided." The fallout from this one box is huge. It becomes a symbol of the measurement problem. Fuels the many worlds idea where the universe splits into branches and rewires how we think about observation itself. And for you, it leaves one nasty little thought. How much of your reality only snaps into place when you finally look? Number 2, the twins who age apart. Imagine you and your twin growing up in the same town, same birthday, same everything. Then one day, you watch them climb into a sleek experimental spacecraft, engines humming with ridiculous power. They wave. The countdown hits 0 and they blast off, circling the Earth at a tiny fraction of light speed while you stay home paying taxes and scrolling social media. Years pass. You get older in the usual way. Wrinkles, gray hairs, knee pain when it rains. Meanwhile, your twin is whipping around the planet so fast that time itself is running slightly slower for them, thanks to Einstein's relativity. Satellites already experience this. Their clocks drift compared to clocks on the ground. In the ship, your twin is living in that same strange slow time bubble. Finally, the spacecraft lands. The hatch opens. You run to meet them, and something is off. Their face looks just a little younger than yours. Not sci-fi immortal, just cheated out of a few years younger. The paradox is brutal. Didn't each of you see the other one moving? Shouldn't their clock be slow from their point of view? Here's the resolution. Your paths through space-time weren't equal. You stayed in one frame. They accelerated, turned, and came back. Relativity doesn't treat those two journeys the same, so your amount of time between goodbye and hello is genuinely different. This isn't abstract. GPS satellites have to correct for this, or your map in New York or Berlin will be wrong by kilometers. So next time you check your phone and it tells you exactly where you are, remember, your location only works because the universe quietly admits that time is not fair and someone out there is always aging slower than you. Number 3, the game show that cheats your brain. You're on a brightly lit TV stage, sweating under studio lights. In front of you, 3 doors. Behind one door, a shiny new car. Behind the other 2, goats that look suspiciously smug. You point at door number 1. The host smiles, walks over, and opens door number 3, revealing a goat. The crowd laughs. Then he turns back to you and says, "Do you want to switch to door number 2? You pause. Your heart is pounding. It feels obvious. There are 2 doors left, 1 car, 1 goat. 50-50, right? You imagine the humiliation of switching and losing, or the cringe of staying and losing. In your gut, both choices feel equally risky. So you might as well hold your ground and look confident. Here's the paradox. The math says if you stay, your chance of winning is 1 in 3. If you switch, it jumps to 2 in 3. When you first picked, there was a 1/3 chance you chose a car and a 2/3 chance you chose a goat. The host reveal doesn't erase that. It just concentrates that 2/3 goat probability onto the one remaining unopened door. You should always switch, but almost everyone's intuition screams the opposite. The fallout from this tiny game show puzzle is deliciously humiliating. When this problem went public, thousands of people, including professors and PhDs, wrote angry letters insisting the solution was wrong, only to be disproven by simulations. It's become a classic example in U.S. and European classrooms of how confidently wrong we can be about odds. And it leaves you with one uncomfortable question. If your gut can't handle 3 doors and goat, how many logical life choices are you messing up without even realizing it? Number 4, particles that talk faster than light. You're sitting at a lab bench, watching a machine spit out pairs of tiny particles that fly off in opposite directions. One heads toward a detector on your side of the building. The other shoots down a long tunnel to a detector far away. Same birth, same moment, then gone like microscopic twins ghosting each other. You flip a switch and measure your particle. In a fraction of a second, your screen flashes. Spin up. At the exact same moment, the other detector, kilometers away, measures spin down. Do this again and again in random directions, and the results are always perfectly linked, as if the particles agreed on a script before they left. Here's the twist. Nothing is telling the second particle what to do when you make your choice. Einstein thought this was impossible, calling it spooky action at a distance, because it looks like information is traveling faster than light. But experiments keep saying, the universe really does allow these instant correlations, even though you can't use them to send a message. The consequence is wild. Our idea that things have local, pre-existing properties just sitting there waiting to be revealed doesn't hold up. At the deepest level, reality seems to care more about relationships than about separate objects, which forces you to ask, what if the universe is less like a bunch of things and more like a single, very weird conversation? Number 5, the hole that eats information. Picture yourself drifting toward a black hole, a dark sphere hanging in space like a hole punched through the stars. Behind you, the universe. Ahead of you, a boundary called the event horizon, the point of no return. You toss in a box full of data, photos, hard drives, everything embarrassing you've ever saved, and watch it vanish past the edge. For years, the story was simple, nothing escapes. But then Hawking showed that black holes slowly leak energy as a faint glow called Hawking radiation, like a campfire dying in slow motion. Given enough time, the black hole shrinks, shrivels, and eventually evaporates into random-looking particles and heat. Here's the paradox. Quantum physics says information can't be destroyed. But if your box falls in and the black hole just evaporates into meaningless static, it looks like the universe has lost the details of what was inside forever. One of our most successful theories says no info loss. Another says, yep, it's gone. And they both can't be right. The fallout from this cosmic argument reshapes theoretical physics. It pushes scientists toward ideas like the holographic universe, where everything inside a region is secretly encoded on its surface, and where space itself may be built out of information. And it leaves you wondering, if the universe treats information as sacred, does that make every choice you make more permanent than you think? Number 6, time's arrow that shouldn't exist. You're in your kitchen, holding an egg over a bowl. Your fingers slip. The egg falls, shatters on the floor, yolk oozing into cracks. You swear, grab a towel, and start cleaning. You don't stand there waiting for the shell pieces to leap up by themselves and reassemble in your hand. Everyday life is full of this one-way traffic. Coffee cools down, ice melts, people age, stars burn fuel. The mess spreads, the order fades, and we call it just the way things go. On paper, though, the laws that control atoms and molecules are perfectly happy to run backwards. If you film colliding particles and reverse the footage, the math wouldn't even flinch. That's the paradox. The microscopic rules are time-symmetric, but your world is not. Entropy, the measured disorder, almost always increases, giving us a direction of time that the underlying equations don't demand. The best explanation so far? The universe started in a freakishly low entropy, highly ordered state and has been sliding downhill ever since. The consequence is that your sense of past and future might come less from some cosmic arrow and more from statistics and memory. So when you look in a mirror and see another year gone, remember, you're not just getting older. Your entire existence is riding a one-way wave of increasing chaos that no one fully understands. Number 7, the ball you cut into infinity. Imagine you're holding a perfect, solid ball in your hands. Not a real football or basketball, but a flawless mathematical sphere. Smooth, uniform, no atoms, no imperfections. Now a mathematician walks in and says, "Watch this. I'm going to cut your ball into pieces and make two balls the same size as the original." You picture thin slices, maybe some clever folding. But that's not what happens. Instead, they slice your ball into a few bizarre, dust-like sets of points, so scrambled and scattered that they don't even have a normal idea of volume. Then, using only rotations and movements, they reassemble those sets into not one, but two identical copies of your ball. Here's the paradox. The Banach Tarski theorem says this is allowed in pure math. You're not stretching or adding anything. You're just rearranging, and somehow you've doubled the object. In the real world, atoms are too chunky and quantum rules step in. So you can't actually counterfeit basketballs, but the math itself is perfectly consistent. The consequence is a disturbing split between the world in your head and the world in your hands. It shows that obvious ideas like volume and fairness can fall apart in higher-level math, and that our intuition is only built for the tame corner reality we evolved in. And it quietly asks you, when you trust something just because it feels logical, how sure are you that your brain isn't secretly doing its own Banach Tarski trick? Number 8, the universe that exists because you're here. Close your eyes and imagine a control room for reality, full of dials. One dial sets the strength of gravity. Another controls how strong atoms stick together. Another adjusts dark energy, the thing that makes space itself expand. Now imagine you, very carefully, nudging each dial just a little in the wrong direction. Suddenly, stars never form, or they burn out in seconds. Atoms don't stay together, or every element heavier than hydrogen simply can't exist. In some settings, the universe rips itself apart too fast for anything complex to happen. In others, it collapses back on itself before you get a single stable planet. The paradox is a fine-tuning problem. Out of all the possible values these constants could have taken, we ended up with a tiny range that allows life and Netflix and coffee. The Anthropic principle says basically, of course you find yourself in a universe that allows observers. Because where else could you be? Some physicists talk about a multiverse full of different dials. We live in the one that isn't instantly dead. The consequence is that why these numbers stops being a simple physics question and becomes a philosophical one. It blurs the line between hard science and uncomfortable cosmic coincidence, and it invites religious, existential, and purely statistical answers all at once. And it forces you to consider, are you living in a specially tuned universe, or just a one-corner reality where someone like you can sit around and worry about it? Number 9, watching reality until it stops moving. You're in a dark lab, lit only by the glow of screens and a single blinking detector. Inside a vacuum chamber, a lonely atom sits in an excited state, ready to drop down and release a photon, like a tiny time bomb waiting to go off. If you leave it alone, it should decay after a predictable average time. But tonight, you don't leave it alone. Instead, you keep checking on it. Rapid pulses prod the atom again and again. Are you still excited? Are you still excited? Each measurement slams the system back into its starting state, like hitting undo on reality over and over, and the decay you were expecting just doesn't happen. Here's the twist. This is a quantum Zeno effect, where constant observation freezes change. The more often you measure the unstable state, the less likely it is to evolve. In the quantum world, a watch pot literally does refuse to boil. Your act of measuring isn't neutral. It's like constantly yanking someone back to the starting line. The consequences go beyond acute paradox. This effect is now a tool for controlling quantum systems, helping scientists keep fragile qubits stable long enough to compute. And it leaves you with an unsettling idea. If watching can stop things from happening, how many parts of your life are you measuring so hard that they never get the chance to change? Number 10, the missing alien neighbors. It's a clear night. You step outside, look up, and see the sky over your city, London, Berlin, Chicago, studded with stars. You know the facts. Billions of stars in our galaxy, billions of galaxies out there, and now thousands of exoplanets confirmed, many inhabitable zones. On paper, the universe should be crawling with advanced civilizations. Now, jump back to a 1950 lunch at Los Alamos, New Mexico. Physicist Enrico Fermi is eating with colleagues, talking about UFO sightings and rockets. He does a quick, nerdy calculation on a napkin about how fast a civilization could spread through the galaxy. Then he asks the question that still haunts us. Where's everybody? That's the Fermi paradox. If intelligent life isn't insanely rare, someone should have colonized or at least visibly modified huge chunks of the galaxy by now. But we don't see megastructures around stars, no obvious probes, no clear, repeating beacon that says, "Hi, we're here." So either advanced civilizations almost never get started, die off quickly, choose to stay hidden, or we're missing some giant part of the picture. The consequences are unsettling and weirdly personal. Scientists use this paradox to think about existential risks, from nuclear war to runaway AI, and to design better searches for life that might not look or talk like us at all. And when you stare at that quiet sky, you can't help wondering, are we the future old ones of the galaxy, or just another brief noise the universe will forget